Okay, Unit 3, Day 1b. So yesterday we talked about some exponential functions. We'd mentioned that like how things spread, like viruses, how they spread, and we can even say like how a rumor would spread would be another common one for this. Starts out exponential, but then actually it changes as more and more people are infected, or more people hear the rumor. Then you can't reinfect them or retell them the rumor, so it starts to level off. And that's what's called a logistic function. So we get into logistics, or they start out exponential. And like here's a simple example of one. It starts out exponential, but as more and more people have, like we said, heard the rumor or been infected, it starts to level off because there's fewer people to tell the rumor to, and eventually it flattens out, where if everyone's heard the rumor or everyone's been infected and no one else can get it, so it flattens out and it approaches an asymptote. So our learning targets here, I will recall the base E and applications of their graphs. Something to think about that. Remember, if you remember from Algebra 2, E is going to be the rate that you use when compounding continuously. Terrible spell. Continuously. It's supposed to be continuously. Or something's growing continuously or decaying continuously. You might say a bank compounds interest quarterly. Well, what if the bank just never stopped compounding it? That'd be continuously. So instead of using a rate to a power, you use e to a power for something that's changing continuously. I can evaluate the logistic function. That's this new guy. I think we introduced the shape earlier in the year when we did our prerequisite unit. And I can write equations for population growth. And this would also be population, of, if you have limited resources, this is how populations actually grow too. On Earth, our population is growing pretty quick. I mean, we're adding 1 billion people every, I don't know how many years it is. In fact, I paused the video and looked this up, and I can't find how often or how long it took to add the last billion. But I know it said that, according to this, that it took about 2 million years for Earth to reach 1 billion. You can argue when Earth started. I don't think we really know that. But it took 200 years to reach 7 billion. So we are growing quickly. We're definitely somewhere in here. Now, as our resources run out, we run out of land to live on and food that the land can supply, and our resources and our water goes bad because we pollute it, and our atmosphere goes bad and lets the sun burn us. We're going to approach up here. We're going to level off, and we can't grow anymore because people are dying as fast as they're being born. So population growth typically starts out exponential, but at some point, if you have a limited land or a limited area that you're living on, it's going to go like this. It's going to make this shape. Okay. Now, we got an example here. So the number of students infected with flu after T days at Springfield High School is modeled by the following function. So it's this function right here. This is a logistic function. It has a number up here. It'll have 1 plus and then some number, e to some number. It doesn't have to have e in there. It can have a different base, and that's okay too. I mean, typically use e because things are growing continuously, but they could just put a number in there too, like 2 to the negative 0.3 power. It could be anything. But this is the function. So they give us the function here. What was the initial number of infections? So on day 1, how many infections were there? Well, for this one, just plug in 0. Plug in 0 for t there. So it would be 1600, and this is population on when time is 0. 1 plus 99, e to the, and it doesn't really matter what I'm multiplying by. If I'm multiplying anything by 0, this is going to be a 0, and 0 power is a 1. So 99 plus 1 is 100. 1600 divided by 100 is 16. So when they started keeping track, there must have been 16 students were infected. So maybe 16 students came to school with this flu. After 5 days, how many students will be infected? So plug in 5. So I'm going to plug in 5 here. I'm going to skip ahead to the answer. It should be 160.3. So you can practice putting that in there. Plug 5 in and see if you can get 160.3. What is the maximum number of students that will be infected? So if you think, if I were to have 1 on bottom, 1 plus anything, what's the smallest the bottom could be? Well, the smallest the bottom could be is 1 if this was 0. And then if the smallest that can be is 1, and I take this divided by 1, the biggest number I can get is 1600. And it just so happens that's always true. The number on top will always be the maximum amount. And that's where, if you look, this is 1500, a little bit above that. That's this horizontal asymptote that's limiting how fast this, or how high this can go. So the maximum number of students going to be infected is 1600, meaning that that's how many students are at the school, 1600. And then according to the model, when will the number hit 800? And we're just looking for an estimate here. So on this graph, here's 500, 600, 700, 800. So I'm going to take this across, bring this down. That looks like, because my grid's not so good here. But we could say 11 or 12 days. So somewhere around 11 or 12 days. When will the number, so I'll again, because I'm estimating here, I could say around 11 or 12. And we could I could plug that in and see. Let's plug in P of 11 and P of 12 and see what we get, see if that's close. Okay, and so I typed it in here, type in my calculator, and then if you go to your window, just think, what X values do I need? Well, in this graph here, it goes from 0 to 30, so I made mine from 0 to 30. And then your Y values, we just said that the 1600 is the most, so I'm going to go from 0 to 1600 for my Y-axis. Push your graph, and let's just start tracing. I'm going to plug in 11 and see what I get. I get 722. I plug in 12. So somewhere between 11 and 12. So, you could say during the 11th day, we'll say 11. So when T equals 11, that's when it happened. By the time the 12th day started, it was higher, but when the 11th day started, it was lower. So, of a group of 200 college men, the number N who are taller than X inches is given below. So there are, out of 100, let's see here. So out of 200, 197 of them are taller than 65 inches. So this is inches, and this is the number of them. 195 are over 66 inches. So that means 2 of them were between 65 and 66. Now, as I get taller, what's going to happen? Well, there's going to be fewer and fewer of them are going to be taller than that height. I mean, only 25 of them are taller than 73 inches. Only 2 of them are taller than 76. 2 out of 100 are taller than 76. So explain why a logistic model is appropriate. Okay, so if we construct a scatter plot of this guy, does it follow that shape, that here I want to say S shape kind of curve here? Let's get our calculators. So I put all my data in, and I made a scatter plot of it. And you notice it is the same shape, it's just flipped. Okay, so this is, it grows and levels off. This one actually falls quickly and levels off at 0. So does it have the same shape? Well, yeah, it's just flipped over. So it is like the parent function. It is that same shape, but it's flipped over. So some big things that make logistics model stand out is the fact that they're bounded above and below. So bounded above and below. Meaning there's 2 horizontal asymptote, and it's contained between those two. So here's a top, here's a bottom. It's contained between those two. And then the end behavior following those asymptotes. And there is a symmetry here about it. Now the symmetry, I'll put a comma here. So the symmetry, symmetrical, it does have an odd symmetry. Odd meaning symmetrical about the origin, but it's not symmetrical about the origin, it's symmetrical about a point in the middle here somewhere. So there's a point here where if I rotate this like fan blades, I get the exact same thing on the other side. Okay, and this is actually on the back side. It talks about where to find that point. Okay, so let's, there's this thing called point of maximum growth, and here's how you find it. given this stuff, and we'll go through this again. I'm just kind of looking ahead. And there's this point right here that if you rotate it about that point, it has an odd symmetry to it. Okay, so you'll see that like rotate 180 degrees, rotate in a circle 180 degrees, and it's the exact same thing. So looking down here, so compare an exponential model versus a logistics model using your graphing calculator. So I'm going to do, I'll go to stat, I'm going to calc, I'm going to do, let's see, exponential regression with those two. I'm going to store this in L1. And the R is not too bad. R squared and R aren't terrible. You know, it's pretty good numbers, pretty strong. But then I'm going to do the same thing. I'm going to do a test with logistic. So there's logistic. Hit enter. Do the same thing. L1, L2. Now here I'm going to store this equation in Y2. So I'm going to pick it. That way I have both equations at once. Calculate. Takes a lot longer. Logistics regression takes a lot longer on the calculator. And it doesn't give you an R. It's very difficult to calculate R, and it's not going to be very helpful to calculate R with a logistic. But now let's graph these guys. So I'm going to go to graph. There's my original scatter plot. The first one is the exponential. Now, how good is that really matching? It's not terrible. It's a little bit off here, a little bit off, a little bit off. But look at this logistic curve. It basically goes through almost every point. You know, it doesn't hit right in the center, but it goes through just about every point. So this one, obviously, logistics is going to be a much better model for this kind of thing. Okay. So backside, here's just some basics. I probably would want to maybe pause the video and just study this too. But there's some things you plug in with every logistic function. Again, there's this number on top, this C, and that is that's like the maximum point. That's the highest it goes. And here it talks about the domain of all real number, I'm sorry, the range of all real numbers goes from 0 to C, and those are the asymptotes. Y equals 0 and Y equals C are the asymptotes. So Y equals 0, Y equals C. There's always going to be a 1. There's going to be a number out front. You could use E. We could also not use E. It's possible to not use E and have like 5 to the 2x or something like that. So we can all, you know, it all depends on that. You can, just like exponentials, you could have E for a base, or you can have any other number for a base too. And then you have the x here that's always here. So y and the x are always fixed. The y-intercept is just going to be what you when you plug in 0 for x. Well, when I plug in 0 for x, 0 times anything is going to be 0, and then a base to 0 is going to be 1. So it's just that 1 plus a on bottom. That's why that's y-intercept. Domains all real numbers, goes left forever, right forever. The graph is increasing from left to right. The parent function is. Now the one on the front was decreasing from left to right, but it's always doing one thing. It's always increasing or it's always decreasing. It's never switching. There is a point of maximum growth, and when we say it, that's like the steepest slope. You know, this is good growth. It's the slope's going up, stronger growth, stronger, but right there is the strongest slope you'll get. After that, it starts to level off, and the slope is changing, where it's getting less and less and less. And then you find that using this formula, if they ask you for maximum growth. Yeah. So let's go down here and do some examples, and we will eventually have you find your own. That's in a later day. Today is just we give you the function, you work with it. So we give you the function, you work with it. So the number of households in the U.S. that own VCRs. Maybe you don't know what that is. I grew up with a VCR. Has shown logistic growth. So in the 1980s, you know, and around, I shouldn't say this, but I was born a little bit after 1980. They were invented. They took off. Everyone owned one, and then eventually DVD players came out, and people stopped buying them. So it's probably actually dropped now. If we had, because I don't know if my family has it. My mom and dad even own one anymore. They probably threw it away because it stopped working, and then replaced with a DVD player. But anyway, so through 1999, we'll just say it's valid for these years, it had this function where T is the number of years since 1980. So in what year were there approximately 86 million households with VCRs? So I'm going to put that in my calculator, so put the function in there. make sure the denominator is in parentheses. So this whole denominator needs to be in parentheses. And we can graph it. And I'll pick, I'm going to pick my window here. Now I pick 0 to 19 because it's from 1980 to 1999. I really don't need to go beyond those 19 years. So 0 being 1980 and then 19 being 19 years later. And then for y min and max, I just picked 0 and I picked 100 as in 100 million. Hoping that catches it. Maybe it's more than that, I'm not sure yet. So, but if they're asking me to find where it's 86 million, that should be on the screen because I'm going to go up to 100 million. So hit graph. This guy. And you can either trace and look for 86, which would be somewhere during the 14th year. So somewhere, let's see, if I type in 15, that's 86.91. If I type in 14, so somewhere during the 14th year. So in what year? It's 14 years later, so it'll be 1994. Let's say 1994. It's during that 14th year that switched over. You could also do a table for this too. You could let your table set up be start at 0, and you could start scrolling down until you get to 86. You kind of get the same idea. Somewhere during the 14th year, it surpassed 86 million. So graph the model and what year did the growth rate of the household stop increasing and then start decreasing. So this is, so in what year we would want to do, I'm going to take the maximum is 91.86. I'm going to take that C divided by 2. So C divided by 2, so 91.86 divided by 2, and that would give me 45.93. So I want to know what X value gives me 45.93. And if you scroll back and forth a little bit here, you could trace 45.93 somewhere here between 7.77 and 7.8. So that's in the 7th year. So when X equals 7, it says in what year? So that'd be 1987. So during 1987, it was just crazy. Like everyone was buying one. And now the next example, we're just simply graphing it. It says find the y-intercept, find the horizontal asymptotes, and then sketch it. So for these guys, again, the y-intercept is going to be c over 1 plus a. So this would be 9 over 1 plus 2. That's just putting a 0 in for this, wipes that out. So this is what's left, 9 divided by 1 plus 2. So that's 3. So I'll say 1, 2, 3. There's my y-intercept. This one's going to have asymptotes. I'll say y equals 0. And then y equals 9. So 3, 4, 5, 6, 7, 8, 9. And y equals 9 are the asymptotes. So if I was going to graph this guy, and this, because we're just starting out here, it's going to be kind of that general S shape. Try to make it, so if I rotated it, it'd look like a fan blade rotating. Looks something like that. That maximum growth is probably somewhere in here. We're just getting a quick sketch of it though. We're not trying to make it look perfect. This guy here, y-intercept, asymptotes. It's going to be y equals 0, as always, for the bottom asymptote. Now, if there was like a -2 on the end of this, you could drop that down, but there's not. And then y equals 8 is the highest it ever gets, because that's the C up here. So 1, 2. Not sure that's drawn to scale, but something like that. And then the y-intercept, just cover that up. So 8 divided by 1 plus 4, 8 divided by 5. So 8 divided by 5 is between 1 and 2, so somewhere in here. Again, I'm really bad at making it look symmetrical, but if I took this fan blade and rotated it about some point somewhere in here, it should look the same on both sides.